Hello friends, this is Rajendra Sawant, professor at Sardar Patel Institute of Technology, Mumbai. Today we are going to study three-phase circuit, its analysis and simulation with SQL simulation tool developed at IIT Bombay. Today specifically we are looking at star connected load and we are going to analyze a given exercise for a star connected balanced load. So friends, consider the first exercise on star connected load. In this exercise, we have been given the line voltage as 400 volts, 50 hertz, and a star connected balance load of power rating 10 kilowatts and 0.8 power factor lagging. And we are asked to find out what is the phase and line currents and also the phase impedance. So specifically, we want to find out what is resistance of this particular phase impedance and inductance of the phase impedance. So mind well, this is a balanced load. So phase impedances are at all the phases, they are same, they are identical to one another. So we shall be dealing with the analysis first, and then later on we'll verify our analysis results from the computer simulation. So let us work out this problem. So we have a star connected system here, and which is a balanced star connected system. So let us draw this kind of structure. So it's a star connected load. Let us consider that our nomenclature for the phases are something like this: A phase, B phase and C phase. So there is a A terminal, okay, where the A phase is connected. Okay, so this we shall call it as a node or A terminal. This is, we are calling it as a B node, and this we are calling it as a C node. Okay, and this we are calling it as a neutral. So this is neutral of the load. Okay, so this we can call it as NL. Now similarly we shall have a system of star connected balanced supply. Okay, so here also we have three terminals. Okay, we can call them as, let's say, AS, BS and CS. Okay, and each one of them is having a single phase supply. Okay, single phase system. This is phase to neutral voltage here. Okay, and if you look at the line, so then it's a line voltage, phase to phase voltage. So now we are supposed to connect, okay, this A phase here to the load. This A phase voltage, let us call it as EA, EB and EC. So EA is connected to the phase of A here at the load, and this line we shall be calling it as A line, okay, whose current is said to be IA, and the second is a B phase. Okay, this is connected here and its current is IB. So this line which connects the B terminal of the source to the corresponding B terminal of the load, and this line carries a current IB, okay, when activated. And the third one is this line. So this is carrying current IC, okay, and the same current is also passing through the phase. So mind well, by way of topology, the line current and the current which is flowing through the phase. Okay, so this we call it as IPH, and this we call it as IL in general. So IL and IPH, they are same by way of topology. But look at the voltages. So this voltage between phase terminal and the neutral. Okay, so they are called as a phase to neutral voltages. Phase to neutral voltage is VAN, VBN, VCN. So these are the phase to neutral voltages. Okay, so let us write down here as VAN, VBN, and VCN. Okay. Now, what are the line voltages here? The line voltages are phase to phase voltages. So this is the one line A, and this is another line B. So line voltage is the phase to phase voltage between A and B. So similarly, we have B to C and C to A. Okay. So this voltage is given to us as 400 volts. Try to understand. Okay. So now we shall summarize this that we have defined IA, IB, and IC as the phase or line currents because they are same. Okay, and we have defined a set of phase voltages. They are VAN, VBN, VCN. Okay, and so these instantaneous phase voltages are called as the phase voltages. Okay, and we have a system of line voltages VAB, VBC, and VCA. These are all instantaneous values. Okay, and they are called as a system of line voltages. Okay, and we popularly know that magnitude wise, the magnitude of VL is equals to root 3 into VPH. This we have studied in the theory class. Magnitude of VPH. Okay, so in general, say for example, if we take VAB, so if you take magnitude of this VAB is equals to root 3 into magnitude of VAN. Okay, and since it is a balanced system, here VAN, VBN, VCN are having the same magnitude and mutual phase difference of 120 degree. Okay. And we have got line current and phase current, they are equal. Okay, that means they are same basically. So therefore, now if we look at the problem which is given to you, so that is P is given as 10 kilowatt. Okay, and cos phi is the per phase power factor, so we can call it as a cos phi ph or cos phi as 0.8, but this is lagging, so that is certainly this is a inductive load. Okay, we have been given VL as 400 volts and 50 hertz, so this value is RMS value. Okay, now we want to find out what is the phase current. Okay, phase current and line current, they are same, so therefore we can now compute here the line current, something like this. So P is equals to, in a star connected system, P is equals to root 3 VL IL cos phi. So this is formula which we have seen in the theory class. Okay, from this we can get IL, which is the same as IPH, which is equals to P upon root 3 VL cos phi. So from this we can directly get the magnitude of IL. okay, from this formula, because P is known to you, VL is known to you, and cos phi is known to you. So if we substitute this as 10,000, okay, and substitute this as root 3 into 400, okay, into cos phi is 0.8, okay. So we shall be getting the appropriate value of the line current or phase current, they are same, okay. So we found that this particular value is around 18 amperes, okay. This is 18 amperes, and its angle is minus 36.86, because cos inverse of 0.8 is 36.86, and since this is lagging, so current should lag, so therefore this is minus 36.86 degrees in amperes. So this is what the current in RMS, okay. So this is RMS current, okay. So we have to verify this current through SQL simulation, computer simulation, whether this the same current is coming or not, okay. Now the another verification which we have to do is the important verification as to find impedance values, to find impedance parameter, okay, impedance parameter. So this is the second step. Now what is formula for ZPH? So consider that per phase equivalent circuit. So what is this per phase equivalent circuit? A resistance, a resistor, inductor whose values, so this is XL equals to omega L, and we are exciting this particular branch by VPH, okay, the phase voltage, and the current which is called as IPH, okay. So from this we can say that, okay, from this we can say that, okay, from this branch, okay, is called as ZPH, per phase impedance. So magnitude of ZPH is equals to VPH upon IPH, okay. And we have already studied what is IPH from the P, okay. So let us find out ZPH as equals to VPH upon IPH, is basically IPH and IL, they are same, okay. And we found that this IL is equals to P upon root 3 VL cos phi, which we have studied, okay. But what is VPH? So VPH is basically VL upon root 3, okay. So this is then can be solved as, okay, this is VL upon root 3 multiplied by root 3 VL cos phi upon P. So this can be simplified as root 3 gets cancelled. So this is simplified as VL square upon P into cos phi. Okay. Now, so ZPH is VL square upon P into cos phi. Very simplified expression. Okay. Now let us go back to the impedance triangle. This is R, this is XL, this is ZPH, okay, and this is phi, power factor angle phi. Right, so we can write down this R as ZPH cos phi, and so this is VL square upon P into cos phi, that is cos square phi. Okay, so we can directly get the value of R. Okay, one can get directly value of XL as equals to ZPH into sine of phi. Okay, or this is equals to VL square upon P into cos phi into sin phi. So sin phi into cos phi. So this is how one can directly calculate XL. Okay. Now once we know XL, one can find out this L as equals to XL upon omega. Omega is basically twice pi F. F is 50 Hertz. So therefore, this is 100 pi. Omega is 100 pi. So therefore, XL divided by 314.159 is nothing but inductance in Henry. So after calculating this, we can go to the SQL simulation. So we found from our computation here that this ZPH is equals to 12.8 angle 36.86. So that is how this 36.86 has come. This is because this is cos inverse of 0.8. So this is in degrees. Okay, so we can convert it into rectangular form and we shall be getting R as 10.24. So this can be written as 10.24 plus J 36.86. Sorry, 7.68. 7.68 ohms. This is ZPH. This is a complex ZPH. Okay. So from this we can conclude that this is R, that is equals to 10.24. Okay. And this is XL. So L can be found from this as equals to. So L we found this L as 24.4 millihenry. Okay. Now how do we verify this by SQL? Okay. After knowing these values, we can in SQL simulation what we shall do, we shall take the source, we shall take the load as a star connected load, we'll substitute these values there, we'll substitute these values, okay, and we'll verify whether the active power generated or active power consumed in the load is 10 kilowatt or not. And what is the reactive power here? The reactive power is basically, if P is 10 kilowatt, then the apparent power is equals to P upon zero point 0.8 because cos phi is given as 0.8. Okay, so this is basically a power triangle. This is P, this is Q, and this is S. Okay, so therefore from this, and this angle is power factor angle phi. So therefore from this we can say that this particular is S is P upon zero point 0.8. So if we compute this, okay, we shall be getting it as 10 upon 0.8. So this is 12.5 kilowatt kVA. Yes is equals to 12.5 kVA. Okay, this is in kilowatt. Okay, then one can find out Q, that is equals to S sin phi. Okay, so therefore this is equals to 12.5 into sin phi is 0.6. So we shall be getting 7.5 kVAR. Okay, so we are getting this P as 10 kilowatt and Q as 7.5 kVAR. Okay, if we can verify from the simulation that the actual power, okay, with by substituting, you know, these quantities in the load branch, if this load branch is drawing the current in such a manner that the power dissipation, three phase power dissipation is found to be 10 kilowatt and the reactive power drawn is also 7.5 kVAR, that means whatever we computed is correct. Okay, so this is known as a verification. So let us go to the SQL simulation. So this is the SQL window. Now here we shall try to understand what we have taken here. The first one is the source. So this is a three-phase source. So this block is called as VSRC-AC3. Okay. So this block has got certain parameters. So what are these parameters? We can see this parameter from this VSRC-AC3.ECE help. Okay. So we can go here and find out that this is a system of three voltages which are connected in star. There is a neutral also, okay, and each phase voltage, okay, or each voltage here in the system of star connected uh, source. VAN is called as the A phase voltage. VBN is called as the B phase to neutral voltage. VCN is called as the phase to neutral voltage of the C phase, and their equation. Okay. So here what we have to substitute is the maximum value. Okay. So what we have to do here, we have to substitute for each of these phases. We have to substitute the maximum value because these are the equations here. Okay. Given, right? And we have to also substitute their phase values, right? This T0 we can keep it as 0, right? So therefore, if we go back here and if you just look at the property configuration panel, so we shall find out that VA, VB and VC are the phase to neutral voltages and its maximum values. Okay, so maximum value of phase to neutral voltage which is given here. Okay, we can find out what is the phase voltage here because we are knowing 400 volt as the line voltage given to us, which is same in all the lines. So this 400 volt, okay, can be computed, uh, can be converted into phase voltage. So phase voltage is found to be 400 by root 3. So 400 by root 3 is basically so this is, so VL equals to 400 volts, which is given to us. So phase voltage is equals to 400 by root 3. Okay, and then we want to know what is the maximum value of this phase voltage. Okay, so this is equals to 400 divided by root 3 into root 2. Okay, so this comes to 326.6 volts because 400 upon root 3 into root 2 is 326.6 volts. So this is how we have chosen in this particular the property as 326.67. Okay, here, and for balanced system they are all equal. Okay, then we have mutual phase difference as 0, minus 120 degree, minus 240 degree. Okay, and the frequency is 50 hertz, right? And the delay time is 0, right? So this is how we configure the star connected source. Now let us look at the star connected load. So this star connected load is nothing but RL load. Okay, R, A, RB, RC. These are the three, resistances. Okay, and LA, LB, LC are three inductors. So something like this. We have a system of a star connected system, something like this. This is A terminal. So resistor, inductor, and resistor inductor. Okay. So this is R underscore A. This is R underscore B. This is R underscore C. And this is L underscore A. This is L underscore B. And this is L underscore C. Okay. So this we can also check out from this help, okay, which is given here. So if you have any doubt on library component, we can go like this. Just right click on the block and on we shall be getting the help of this particular component. So this is basically the component, okay, as I have already mentioned, right? So therefore, this we already found. R underscore A we found, L underscore A we found. Okay, we have to just substitute the values over here. So we have substituted the values for a 10 kilowatt 0.8 power factor load as 10.24 as the resistor values and 24.4 millihenry as the inductor values. Okay. Apart from that, let us look at the instrumentation here. So we are measuring three phase voltages from these three voltmeters, okay, and three line voltages from these three voltmeters. So this is essentially a meter which is called as voltmeter underscore scale. Okay, so we can find out voltmeter underscore scale from here. From the GME. Okay, so here there are two nodes which are electrical nodes, but one is the general node, right? So this we can configure. So we are calling this general node of the first voltmeter as VAB as the line voltage, VBC as the another line voltage, and VCA is another line voltage. Similarly here it is VCN, VBN and VAN as the phase voltage system. Okay, then this current is IA, okay, which is also designated as IA here, okay, IB here and IC here. Okay, so these are the three line currents, and the same system, same current would also flow through the individual phases. Now let us look at how we are connecting power, how we are computing the power with the sequel. So we have got a general element here which is basically called as a power meter underscore 1, and this can be found from GCE. Okay, so just we have to power, type in power, okay, and go to the GCE and select this. Okay, if you select this here, okay, we shall be getting this block. Okay, but what is this block? So this block can be studied something like this. So here what is being told that there are two components here. One is product of sum of products, okay, and second is the filter, okay, in order to smooth the characteristic. Okay, so the first part is basically the part which computes power, instantaneous power, and then this power is being filtered out later. Okay, so in this case this is a terminal which is supposed to be a first terminal of the voltage. This is second voltage terminal, and this is the third voltage terminal. Okay, then what is the active power? Active power is equals to the summation of three products. Okay, so what are these products? We can explain here as computation of P. So we have VA, N, VBN and ICN as the VCN as the three phase voltages. Okay, and we have VAB, VBC and VCA are the three line voltages. Okay, and we have IA, IB, IC as phase or line currents. Okay, then how do we calculate P? So P can be found by this equation as instantaneous products of VA, IA plus VB, IB plus VC, IC. So this VC is VCN, VB is VBN, VA is VAN. So multiply the A phase voltage and A phase current. Multiply B phase voltage and B phase current. Multiply C phase voltage and C phase current. Okay, and take the summation. So this gives me the active power. Okay, if the system is balanced, we shall be getting a DC here. Okay, otherwise we'll be getting the oscillations like this. Okay, but we are considering this discussion is restricted to balanced system. So what is Q? So Q is equals to 1 upon root 3 times. So now the current IA, okay, is the current which is supposed to be multiplied with the voltage. Okay, then this current IB supposed to be multiplied with another voltage. Okay, and this current IC is supposed to be multiplied with another voltage. Now this voltage should not be the phase voltage, it should be the line voltage. But which line voltage? This is the line voltage which does not belongs to a node. Okay, so that means VBC. Okay, IB into VCA. Okay, IC into VAB. So this is the line voltage and the line current. Okay, multiplication of line voltage of BC and current as a phase or line current as IA. Okay, and similarly here, right? So you calculate three products, okay, of instantaneous quantities and take their summation and divide by root 3. So 1 upon root 3 is basically 0.57735. Okay, so this gives me a Q which is supposed to be a DC quantity, okay, if my load is balanced. So this is my Q, right? And if the load is unbalanced, then I shall be getting the oscillations in the Q waveform, right? So here, if you go back to our SQL simulation, what we have done, in order to compute Q, we have taken the same power block, power meter, okay, and if you just recall the equations, okay, so IA should be multiplied with VBC. Okay, so here VBC is connected and here IA is connected. Okay, the second is equation is VCA into IB. So this is the second product of instantaneous quantities. And third is IC into VAB. Okay, so this sequence must be maintained. Okay, now whatever we are getting is basically this particular bracket. So this bracket. Okay, now multiply it by 1 upon root 3. So that is 0.57735. So because of that requirement, we have taken one scaling multiplication scaling factor, MULTSCL block. Okay, this you can find from. So see here, this is basically 0.57735. So it has got a scaling factor as 0.57735, and this is a multiplication and scaling block. Okay, so this can be found from GCE, okay, library. So general element library. Okay, so it is accepting input as a general variable and output also as a general variable. So it is producing output which is, let's say, Q. Okay, so here we are getting a output as a Q, right? Now let us try to work out this simulation. Transient simulation is being carried out where backward Euler method is chosen. Start value is 0. Okay, end value of the time is 200 milliseconds. Okay, so we are simulating this circuit for 10 cycles of the utility voltage waveform. Okay, and here we have selected two output files. One output file would gather the information about the phase or line currents, the phase voltages and line voltages. And the second is just gathering information about P value and Q value. Okay, so here we have to compile this circuit as circuit file, generate circuit file, run solver. Okay, and let us see first how the system of voltages look like. Okay, so here we find that VAN, VBN, VCN. So these are basically the source voltages. This we have assumed to be balanced because their magnitudes are same. And see here, so magnitude is around 326.6. Okay, and they have mutual phase difference of 120 degree. Okay, and if you go back to line voltage, VAN, VBN, and VAB, VBC, and VCA. Okay, so this is a system of line voltages. Here we shall be getting three balanced line voltages, so which are having this amplitude root 3 times greater than the uh, phase voltage magnitude. Okay, amplitude. Okay, so this is around 566 something. Okay, because it's a peak value. All right, so this is 566. Where how it has come? So this is basically 400 into root 2 is 566. 400 is the line voltage RMS value. Okay, so this we got. Now another point which you have to see as how we relate the phase voltage and the line voltage. So this is a clear difference between the phase voltage and line voltage. So here you can observe that this particular characteristic graph, red graph is basically VAN and blue graph is basically the line voltage, corresponding line voltage, which is VAB. Okay, so VAB is leading the phase voltage by some angle, that is 30 degree. Okay, this we can observe. Okay, another thing is this amplitude, okay, is root 3 times lesser than the line voltage amplitude. Okay, this is root 3 times, so this difference is clearly visible. Okay, so this is what we have to conclude from this. And another thing is, what is the line current and corresponding phase voltage, how it look like? So this is the relation. So we found that this current is very small, okay, but it is lagging. So this blue graph is the current graph of the respective phase voltage. Okay, VAN is the phase voltage and the respective current in the phase is IA. So this current is IA and the red one is voltage. And so this current is essentially this much. Okay, so this is around 25.5. So this is the same as what we computed. Okay, from this 18 into root 2. Okay, so this current is lagging because the load is inductive. So with reference to voltage, this is the age for the voltage and this is the age for the current. So current is lagging behind the voltage because the nature of the load is inductive. Okay, Let us look at the power drawn by this system. So we found that these are the graphs for the power. So these graphs show me that the active power has turned out to be, this blue one is active power, has turned out to be 10 kilowatt. Okay, it is apparent from the graph. And this particular red colored or magenta colored graph is Q, that is the reactive power, and this turned out to be around 7.5 kilowatt. Okay, so this is exactly what we got from the theoretical analysis, right? And this also tells me that whatever parameter values, okay, I have substituted here, okay, as a star connected load, okay, these parameter values are correct, okay, to the extent that this star connected load is taking up 10 kilowatt load from the mains as an active power consumption, and reactive power is basically 7.5 kVAR. Okay, so this validates our design or our analysis. So this is all about star connected balanced load system, which is fed from a star connected balanced supply system, right? Thank you for watching.